So yeah, we're just playing around with the technology here. I see at the moment on the screen, we've actually got Chris's video up top as well as mine. So yeah, maybe we just want to let Chris know that we can still see him at the moment. But I'll get started and stuck into the news for now. So let me see if I can get this started. Okay. Cool. So yeah, we're just playing around with the technology here. I see at the moment on the screen, we've actually got Chris's video up top as well as mine. So yeah, sorry. Maybe we just get a bit of feedback there. We can still see him at the moment. But I'll get started, and I think it might be coming in from your end, James. You might need to mute. Go. Yeah. Okay. Cool. Sorry about that, everyone. Technical difficulties, but astronomy news. So let's start with what's been happening recently in space and astronomy. So at the moment, if you go outside and there are no clouds, you might be lucky and you might be able to see a rare flower moon, supermoon. So this rises tonight. It actually rose at 5:30 p.m. and will remain in the sky for the entire night. So it might be something for us to look forward to afterwards. That's if there are no clouds. So what is a supermoon? Well, that's when it's a full moon, when the moon is at its perigee, which is its closest point to Earth. Because obviously the moon's orbit isn't exactly circle. It's a bit of an ovoid, oval like that. And there is a point where it's furthest away and a point where it's closest. So when it happens to be a full moon and it's close to the Earth, we call it a supermoon because it looks slightly bigger. This is going to be the last supermoon for this year. So this is also known as the flower moon, which is the first full moon in May. So this name comes from the northern hemisphere, where around this time, you might start to see the first few flowers. So something to look forward to for us in the sky tonight. Also regarding the moon, newly discovered ridges on the surface could be signs of recent tectonic activity. So for a long time, we've thought of the moon as being dead, basically a dead rock, no further activity or movement. However, new studies show that it's possibly still tectonically active. So the way they've come to this conclusion is that the moon's surface is mostly covered in lunar regolith or moon dust. However, and they've discovered new ridges that show exposed bedrock with no regolith, so there's none of this moon dust covering it. And when we look at geological time frames, when we're talking about thousands and millions of years, the regolith builds up rather quickly. So the fact that we've found ridges that don't have regolith means that these ridges must have formed relatively recently in terms of geological time frames. So this challenges some of our current thinking about the moon being dead, and it could mean that there is tectonic activity on the moon. Also in recent news, we've discovered the closest black hole to Earth, and it was found in a nearby system. It's a system, I don't have it in my notes, I think it's HR161 or something, but it's a system that we've known about and we've been observing for a while, but we just missed it. So this particular system is 1011 light years away from Earth, and the black hole is locked in orbit with two visible stars. So in this image, this is an artist's impression, the red circle here is the black hole, and these are both stars. So these two sort of orbit around, and this other one orbits around here. It's estimated that this new black hole is 4 times the mass of the sun. And yeah, this is now the closest black hole to Earth that we know about. The next closest black hole is around 3,000 light years away. So this has pretty fundamentally changed our understanding of where black holes are. Because if we found one this close, the thinking is, well, maybe our galaxy has a lot more black holes than we realized, and we just haven't discovered them yet. Also in the news, NASA develops a new ventilator for COVID-19 treatment. So I think this is a great example of technology and engineering changing focus to help out with, the most urgent need at the time being. So they've come up with a new design for a ventilator, pictured here. This is the team that worked on it, and they've nicknamed it Vital, ventilator intervention technology accessible locally. It's quite a mouthful. It makes me wonder if they came up with the snappy word first and then worked backwards to fill in all the gaps. Now, this ventilator isn't designed to be one that can be used for a very long time. The idea is that this is good for really short-term use. Should last 3 or 4 months and then start to break down. But it's the sort of thing that you could use in field hospitals and things like that. It was developed in 37 days by engineers at the Jet Propulsion Laboratory in NASA. And the prototype has passed the test. It's now FDA approved. And the next step is to start manufacturing this to help with the current crisis. I was also reading that the engineers that came up with this have said that the designs for this are royalty-free. So basically, they've come up with this really cool new way to make ventilators, which requires less material and less time. But rather than, I guess, sort of hog that, they decided to share this new information with the world to help everyone build these ventilators more quickly. And speaking of COVID-19, the air in planet Earth continues to get cleaner because of some of the reactions to COVID-19. So we're seeing a drop in fossil fuel emissions. Now, this is because obviously around the world, a lot of us are inside. Fewer people are on the roads, fewer cars, leading to less pollution. So I was reading that the world's response to this pandemic it's sort of an unintended experiment. You know, none of us wanted this to happen, but now that it has happened, it's leading NASA scientists and others to sort of look at what's useful information that we can gather during this time period. So NASA satellites are now monitoring the drop in pollutants so that we can see the effect on the atmosphere. However, it looks like a lot of these improvements may only be temporary. So once, you know, lockdown or things like that end, once the world goes back to, I guess, a sense of normalcy, unfortunately, a lot of this pollution might come back, but we'll see. We now have the earliest evidence of a person possibly being killed by a meteorite. So meteorite deaths is one of these weird things because throughout history, there have been many claims of people being hit and killed by a meteorite, but there's no hard evidence to back up these claims. So strictly speaking, from a historical point of view, we can safely say that no one has actually died from being hit by a meteorite that we know about, that we have evidence for. However, this could change because there's new evidence from the Turkish State Archives that describes a situation in Iraq, August 22nd, 1888, where a man was hit and killed by a meteorite. So this is just the first bit of the evidence. This same team, they want to continue searching these archives to see if they can find another source of information to verify this. So for example, maybe if they can find a letter written by someone around the same time period that also verifies that, then that will make us more confident to say that we finally have the first confirmed death by a meteorite in history. Speaking of mysteries, there's been some new discoveries to do with Venus's atmosphere. So Venus rotates rather slowly compared to Earth. It takes 243 Earth days for the planet Venus to spin around its axis once. However, its atmosphere rotates a lot faster than the surface, about 60 times faster. So in 96 hours, the atmosphere goes all the way around the planet. So this is called atmospheric superrotation. And we've also seen this on other worlds, such as Saturn's moon Titan. Now, new research into this has shown that this could be due to thermal tides. So it's all to do with the way that the solar heat heats up the equator, causing various sorts of flows in the wind and changes in atmospheric pressure. And that could be what's causing the superrotation. They also found that this is what transports heat to the night side of the planet. And so the thinking is that the heat distribution on other planets that have atmospheric superrotation might also be equally distributed. This could provide hope for the future habitability of tidally locked exoplanets. So when we discover other planets, some of them are tidally locked, which means that the one half of the planet always faces the sun, its sun or its star, whereas the other half of the planet always faces away. And we've long thought if we ever found a habitable planet like that, chances are we'll have to have our settlements on the boundary, because you might imagine the half of the planet facing towards the sun might be too warm, the other half might be too cold, so we'll just have to settle in this sort of long strip. However, the new discovery to do with these thermal tides could indicate that on other planets that have atmospheric superrotation, this could actually help spread the temperature around. So even on a tidally locked planet, we could find that the side away from the star isn't as cold as we thought it was. And here's an interesting image for the week. So this is a detailed new view of Jupiter's moon Europa. Now this isn't a newly taken photograph. This photo was from a previous mission to Europa, but the first version was sort of grainy and black and white. But now the research team behind this are sort of going through some of this data, wanting to find out more, and they've taken this old image and enhanced it. And it looks really cool. So this is what we're seeing, is sort of tracks of ice, blocks of ice that move around and then moved about and leave these sort of tracks. It's quite an interesting terrain. You see it from here. And finally, this week in space-related news, Elon Musk and his partner have a new son who they've named XAEA-12. I have no idea how to pronounce that. Apparently this isn't a joke. Apparently this is Musk's name for his new son. So his girlfriend Grimes gave birth on May the 4th. They've announced the name via Twitter. There's no confirmation on how it's pronounced, or even if this is for real, if it's some weird joke or publicity stunt. And also the state of California has said, well, you can't put that on a birth certificate because legally names must be comprised of only the 26 letters of the English alphabet, which is a bit restrictive if you ask me. But anyway, yeah, a bit of lighthearted things to finish off the space news. In terms of upcoming events, we still have a couple of astrophotography competitions running at the moment. It might be hard to take photos for some of these. So the particular one here, the Great Barrier Astrophotography Competition, I believe the photos need to be taken on Great Barrier Island. But yeah, that's something which in future, if we change the lockdown, then that might open up the possibility to do that. But there's also the 2020 New Zealand Astrophotography Competition. And if you're fortunate enough to live somewhere with a nice dark sky in your backyard, then perhaps this is something you could do now. So that wraps up the news and events for this week. So now I believe we'll pass on to our main speaker for the evening, Chris.
Hey guys, am I all go now? Share screen. Oh, how's that look, guys? Okay, we ready to rock and roll?
Yeah, let's go for it.
Okay, well, good. Hi guys, good evening. Welcome to another one of our YouTube adventures here during the lockdown mode, and we're going to have a fun-filled evening of introduction to astronomy this evening. The orders are from high levels to make it fun. You're probably thinking, oh, high levels, Jacinda. Nah, we're talking much higher levels than that. We're talking the president here. The president of the Hibiscus Coast Astronomical Society has given me orders to make sure we have fun tonight, and we'll do it. We will. So let's get going. Just a bit of housekeeping. Any questions related to this evening, just put them in the chat area, and James will see to those later on at the end of the presentation. James will run through them one by one and we'll talk about those. So let's get going. Okay, yeah. So I've got this drinking mug in my hand. Put it up to the camera and you'll see there's a man in a spacesuit there. It's my space mug, my favorite mug. And here's a little bit of a competition for you. Name this pioneer astronaut. I'll give you a bit of a clue from the 1960s. This was sort of a key flight, an experiment. If you went to Jay's talk last year on spacesuits and paid attention, this should be easy for you because this was one of her presentation cases. If you weren't there, or you were there and you didn't concentrate and pay attention, well, tough shame on you. But anyway, we'll have a bit of fun and we'll look at this later on. So if you know the name of this pioneer astronaut, just put his name in the chat. And James, if he sees the correct name come up, he will certainly put that in there. Yes, we've found ourselves a winner. And the winner will get
Chris, we already have a winner.
Oh, really?
So John Burkett correctly said Ed White.
Oh, fantastic. So we have a winner, guys, John Burkett. So John, our next meeting when we do when we do meet up in all person and stuff, back to meetings, which we will not be doing until we feel 100% it's safe for everyone. But when we do, you'll get yourself a chocolate bar. It will not be a pineapple lump chocolate bar, because I find when those things leave the stores, they have a very short half-life. So it's going to be some other flavour, but we'll get you one. Right. Now, tonight's talk, we're going to discuss a lot of principles, scientific and astronomical principles. So I'm purposely going to go slow and methodically through it, and also to have a little bit of light-hearted chat and stuff as well. So we'll see how we go. So tonight's talk is titled Novae, Supernovae, and Kilonovae. What's the difference? In other words, what are the different mechanisms that cause these big notable events that we witness in the universe? Why have I chosen this subject? Well, it's really bugged me. You see in the media, newspapers, books, films, and so on, documentaries, they have nice big flash pictures like this one here, big explosion going off, big supernova remnant here. This is an X-ray image of the Crab Nebula. You might see a new big flash star shining here, but they omit to tell you the actual mechanism that's going on behind it, what's causing it, and how they all differ and contrast. So that really leads on to some interesting questions. How do novae, supernovae, and kilonovae differ? Without a doubt, you've heard those terms being used, without a doubt, out there. So how do they differ? And then as for supernova, everyone uses that term very loosely. Are there different types of supernovas? Let's find out, shall we? So there's two key messages that I want to impart this evening, if you're going to take something home, is that novae, supernovae, and kilonovae are different beasts. Don't get them mixed up. They're different. And as for supernovae, there are four main types. There are actually all sorts of subgroups in that. Don't get complicated or bogged down with that. There are just four main types of supernovae, which we will discuss. I hope to achieve this by breaking the talk into 5 main chapters. First one, introduction and some background knowledge in the context of this topic. Then we'll talk about classical and dwarf novae, what they are and the difference behind them both. Chapter 3 will be type 1a supernovae. Chapter 4 will be type 2, 1b, 1c supernovae and hypernovae. Sounds interesting. And then chapter 5 will be kilonovae. And then if you like a chapter 6, of course, we'll wrap it up and sum it up and bring it together into a nice picture. And then we'll go over that Ed White slide as well. Congratulations there, John, on winning that. Okay, so chapter 1, introduction and background, relevant information in this context. I'm going to mention about the definition of nova. Then we'll cover a broad classification of novae, supernovae, and kilonovae. And then really, I want to briefly talk about stellar corpses. That's what's left over when a star dies in the context of these events. I think that's important to run through what they are. The next talk that I do for Society will be an entire 1-hour talk just on stellar corpses. But I think it's important just to briefly mention what they are now, so it all comes together in your mind. Okay, nova. Nova is a historical term. It actually just means literally new star. Hundreds of years ago, or 1,200 years or so ago, the astronomers of the day would see suddenly a small star would suddenly get brighter for a few days, or they might see where there was no known star, they'd see a star appear for a few days and disappeared, and they just called them nova, or the plural is novae. So it's a historical term, and it refers to a sudden and a transient appearance of an apparently new star. So that's how it got the name. So a broad classification of these events. Really, the main thing, you look at the slide, you think, whoa, that looks a bit crazy. Trust me, at the end of this evening, that's all going to make sense to you. It's all going to be good. So the main two take-home messages from this slide is first of all, there's three major groups. There's your Novae, which we're going to talk about shortly, classical and dwarf, your Supernovae, and your Kilonovae. And the Supernovae there, here's your four groups. They are classified by what elements are most prominently seen in their spectra. What does that mean? It means when you put your telescope and you're looking at the supernova, the remnants of the explosion, and the explosion itself, if you can, if you're lucky enough, but the immediate aftermath, you put your spectroscope on it. And if you recall, a spectroscope picks up the fingerprints, the spectral, the energy fingerprints of each particular atom or element that's there. So it tells you what elements are most prominent in the aftermath of a supernova explosion. And it's from that information that they classify these different types of supernovae. So that's the main take-home message there, and we'll go over it with more depth through the talk. Now, a little bit about stellar corpses. So I've broken it down into three. This is an important little way of remembering things. Stellar masses, a solar mass is the mass of our sun. It's called a solar mass. It's about 2 times 10 to the 30 kilograms, just known as 1 sol. So a planet, or rather a star up to about 8 solar masses, when it's finished its life, it's finished burning hydrogen in its core, then it turns into a red giant. But in its last few stages of life, what happens is the outer layers just gently puff and blow off. It takes about a few thousand, maybe up to 10,000 years for that to occur. That's a short time. It's a long time for you and I, but it's a short time for these stars. The outer layers just quietly blows off, and it leaves the central middle core, which is made up of carbon and oxygen, exposed. And presumably you guys can see my little cursor here. So right in the middle there, they call that a white dwarf. And a white dwarf is a small, compact, very dense, inert object of carbon and oxygen. It's usually about the mass of one sun, one solar mass, and the size is usually about the size of Earth. So it's pretty dense. In other words, the sun condensed to the size of Earth. So it's pretty dense. And there it is sitting right there. That's called a white dwarf. So that is the stellar corpse of a star up to about 8 solar masses. So naturally, you can infer from there that's going to be the fate of our sun in about sort of 6 or 7 billion years' time. The other thing I've made a note here is these, when you see these pretty pictures in books, and you will, that's the Eskimo Nebula, that one there, these are not supernova explosions. That's really important to know. They're called planetary nebula, and you might say, well, God, where's the planet in there, guys? Once again, astronomy is riddled with historic terms that tend to be a little bit misleading because they looked at it a couple hundred years or so ago, and they thought a planet was involved in that when they looked at it through their telescopes. Then, of course, we've discovered it's not, but the name planetary nebula is just stuck, and that's what they're called. So 2 key points there is that it's not a supernova explosion. It's a gentle shedding over thousands of years of the outer layers of a star up to 7 solar masses, and it's got nothing to do with planets. So stars from 8 to 20 solar masses, when they turn into red giants, and we're going to come to it shortly, then they go through the red giant stage, and then they end their lives, which we're going to talk about, their core collapses. We'll talk about that shortly. But they go supernova and they explode. What is left over in the middle is a neutron star. And there it is. This is an X-ray image taken with the Chandra telescope of the Cassiopeia A supernova remnant. And right in the middle there, you can see that little dot there. That's the neutron star in the middle of that supernova remnant. A neutron star is even more dense. It's usually, once again, the mass of about 1.5 up to about 3 solar masses. And it's squashed into the size of a small city, about 20 kilometers diameter. So that's the most densest thing known, densest astronomical object, next, of course, to the black hole, which is a point of singularity. So that there is a supernova remnant, or the aftermath of a supernova explosion. So stars from 80 to 20 solar masses, they're the ones that go supernova with a central neutron star. So you might say, what happens to stars greater than 20 solar masses? They too end their lives as a supernova, a big messy remnant, as you can see there. But in the middle, instead of having a neutron star, they have a central black hole, which is a whole different talk now. The point of this little bit here was you got familiar with the terms white dwarf and neutron star, because they are the key stellar remnants that we're going to talk about. In particular, white dwarfs we're going to talk quite a bit about. They're the end product of stars. White dwarf from a star up to 8 solar masses. Neutron star is the remnant left over from a star 80 to 20 solar masses. Sorry about the repetition. Well, I'm not really sorry, but I think it's important just to really make these key points home. They're probably terms you've heard before. I'm trying to repeat them so everything fits into context from previous talks, future talks, later in this talk. Just want to bring all these terms together. They're all the same. Let's move on. I think we're going to finish this chapter now. Oh no, we've got one more slide here. Now, I put this into a diagram. I think this diagram is important. And you'll see it once or twice later on and again in this slideshow, and I'm going to make a habit of putting it as many presentations as I can. It brings together nicely how different star groups behave and how they progress throughout the evolution and how they die. So you can see here, this is an average star up to 8 solar masses. For example, our sun at 1 solar mass. Goes through its life. After the main sequence, it turns into a big fat red giant. And then slowly those outer layers puff off over a few thousand years to form that planetary nebula and that central white dwarf, which is hot. They get up to surface temperature of about 30,000 degrees Kelvin. Kelvin's the same as Celsius as far as you need to concern. Don't worry about that. But the hot and the compact and the really, really dense and the small, that's important, as you're about to find out in the next chapter. So remember that. Stars greater than 8 solar masses, massive stars, they turn into red supergiants, real big fat things in these later stages of their lives. For example, Betelgeuse, which has been in the news recently, is a super red giant. If you put that in the middle of our solar system, its surface would go out to the orbit of Jupiter. It's that big. These babies go in their lives with one mighty big bang, the supernova, which we're going to talk about. Remember, stars 8 to 20 solar masses end up, the corpse, if you will, ends up as these neutron stars, very, very, very compact. And of course, the ones over 20 solar masses end up as a black hole. So those are the relevant stages. It's just nice to bring those things together, just repeat them over and over again. So when a term gets mentioned, you instantly know what it's all about. Oh, hey, I spent a bit of time preparing the slides this afternoon. Everyone needs a wingman when they do these big jobs. This was my friend, my best buddy, Boston. He was today's big helper. As you can see there, he is just exhausted. He is just totally stressed to the max. You know, brainstorming with his dad, throwing ideas out there. Repeat that one, Dad. Yeah, mention the white dwarfs. And there he is, absolutely exhausted. He's just spent himself with so many new bright ideas. So if you wonder where all these slides come from, they come from the help, my sort of main brainstormer, Boston. Big helper. Thanks, Boston. Right, now we move on to the next chapter. Classical and dwarf novae. So as you can see there, novae are split into classical and dwarf. They both occur when you get a close binary between a white dwarf and a large main sequence and red supergiant. Okay, let's back up. Let's talk about these now. What is a close binary star system? Our sun is a solar star, just chugging its way through the galaxy like that. That's the exception. Most stars are actually in a star system, 2 or 3, sometimes 4 or more stars, and they're all gravitationally bound. And they all go around a common gravitational point, like a binary, as the name suggests, is 2 stars. And as they go around the galaxy, they're quietly orbiting around a central gravitational point like that. And a close binary means, instead of being loosely gravitationally bound, like sort of like yay, they're really relatively tight. They're critically tight, nice tight orbit around that central point or around each other as it appears. So if you get with a white dwarf, it's got to be a white dwarf in the system. So if you get one of these guys, hot, compact, dense, and its in a close binary partnership with a red giant, a red supergiant, or a massive star. In other words, one of these three really big bodies with this tiny little wee white dwarf, that's when you start to have some fun and some sparks fly. So let's move on and talk about classical novae and dwarf novae. So what happens is when you're in this close relationship, close binary stellar system, here is your white dwarf here. Here is your big red supergiant. And remember, the outer layers of these guys are all hydrogen, loosely gravitationally bound. A bigger star is, and I explain this later on, bigger stars have trouble hanging on to the outer layers. Two reasons. One is the surface gravity is low. Your surface gravity is stronger the closer you can get to the center point of an object. So it makes sense, something bigger and bigger, its surface gravity is loose. You've got less control over those contents. And also you've got tend to have nuclear reactions going on in the outer shell. So drives big stellar winds and so on. So these big babies here, they've got very loose fitting outer shells of hydrogen. And you get to a close relationship with a white dwarf sitting in here. What happens is the outer layers of that red giant, through gravitational forces, spill over towards the white dwarf. Now, what happens is that it doesn't just flow straight over, get gobbled up, gobble onto that white dwarf. Instead, it forms an accretion disk. It's just the laws of physics, the laws of motion. That's what's happened. What holds that accretion disk in place is, remember we said that white dwarf was really compact, small radius, the mass of the sun put into the size of the Earth. And what did we just talk about? The closer you are to a center of something, its surface, the stronger that gravity is. So it's really strong surface gravitation on this white dwarf. So it has no problems. Just if it's close enough, it'll just suck in that hydrogen outer shells of this big red giant that's close to it, put it into accretion disk. The other thing about that disk to mention is it heats up, it gets very hot. Well, for starters, it's got about a 30,000 surface degree, white dwarf sitting right here. But the other thing is a law of physics called Kepler's laws of planetary motion. And this law says that if you get a disk of material going round and round an object, the material going around in the inner aspect is traveling a lot faster, a lot higher velocity than the material a little bit further out, than the material further out here, and so on and so on. So the further you go in, the faster stuff is going round and round. The further you go out, it's going round slower and slower and slower. And what that does, which that implies, is all these different layers of radii for your accretion disk, they're all going around there at different velocities. What does that mean? You're getting rubbing and friction. We're talking about high velocities, large amount of material going around this real central dense white dwarf. That disk heats up. So you've got the outer layers of the red giant spilling over to form a hot accretion disk around a white dwarf. Action's already starting to take place, guys. We're having fun. Okay, that disk, what happens then is this, once again, because of the gravity, the material in the inner part of the disk does start falling in towards the surface of the white dwarf. And as we've said a few times now, huge gravitational forces holding things down to the surface of that white dwarf. So that hydrogen that slowly works its way through the hot disk till it gets to the inner part of the accretion disk to then fall onto the surface of this white dwarf, it starts getting really compressed. And what happens when things get compressed? They get heat up. They get hotter and hotter and hotter. So you then end up this ongoing process. You've got this white, dense, hot white dwarf, and you've got this, let's call it an atmosphere, a dense, thin atmosphere around the white dwarf that's starting to get hotter and hotter and hotter. Whammo, you reach a critical temperature whereby that hydrogen ignites and starts fusing. And it's a chain reaction. So you get what we call runaway hydrogen fusion. Hydrogen starts fusing together under these conditions to form helium, which releases energy. And as we know, that's what's happening in the core of the sun. That's what powers our sun, is this whole process. But you've got this fine, thin, hot, compressed atmosphere of hydrogen around this hot central white dwarf. It just ignites, goes bang, you get hydrogen fusion. It just chain reaction, the whole surface of the white dwarf just goes bang, and you get this huge, big flash, sudden release of energy. That, my friends, is a novae, a classical novae. That's it here. Now, here is a Hubble telescope picture. It was taken pre-optic repairs. You'll probably recall when the Hubble was launched from the Challenger space shuttle, 1990. They found it had some optical problems, which they repaired. So this is one of the early photographs, a little bit fuzzy, but look what's going on here. Here's your white dwarf. Here's, look, a nova's occurred to that outer thin atmosphere of hot hydrogen fusing into helium, and it's starting to expand out as you're getting nuclear fusion, that sudden release of energy. And here it is a few days later, getting expelled into space. So that's called I suppose you call that, looking for a better word, a Novae remnant. You've heard of the word supernovae remnant. This is a Novae remnant. How cool is that? Okay, and one of the key things here is that mighty explosion. That was just the atmosphere, if you will, over the surface of the white dwarf. The white dwarf survives the surface explosion. In other words, it lives another day. You've still got your red giant just next door to it. The accretion disk continues on again, a new accretion disk forms, and the process reoccurs. That's really important to know, as opposed to your supernova, which everything goes west. So there's often some frequently asked questions. How bright do these novae get? How long do they glow for? How often do they occur? What's their frequency? So let's have a look at some of these. This is a light curve of a classical novae. And what a light curve is, you see a lot of these in astronomy. Let's have a look at one for starters. So what happened here is you've got an astronomer. He's got there's a novae happening. So he points his telescope there and he measures how bright that nova is at that moment in time. And he plots it on the right-hand column. And it could be, he could plot it as magnitude, he could plot it as luminosity. Luminosity is just a fancy word for brightness, and they tend to relate it to the luminosity of the sun. Remember that the mass of the sun, 2 times 10 to the 30 kilograms, is just known as 1 solar mass. Same with the sun. The sun's got a set luminosity, and that's just called 1 solar luminosity. So they measure it against either a magnitude, or they'll measure it against luminosity. It's you can do what you like there. You then plot it over various time frames, over a few hours and a few days, and you plot it with time, of course, on your x-axis. So this is what it looks like here. You see the brightness going up, 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 up. Whoa, wrong slide. See it going up and up like that. And it peaks, typically, everyone's a little bit different, but typically a nova will peak brightness at about day 6. How bright? Usually about 100,000 solar luminosities. In other words, you know how bright our sun is in the middle of the day. You imagine something 100,000 times more brighter than that. You think that's bright? You ain't seen anything yet, guys. Wait until we get to 1A supernova. That will, excuse the pun, blow you away. Anyway, let's, so there's your peak luminosity. Then that usually fades over about 4 to 6 weeks. How often do they occur? They typically occur about once every 10,000 years for a new accretion disk to form, the atmosphere of hydrogen to build up and get compressed to a critical level around that white dwarf. They can occur within 100 years, but typically, you're talking a few thousand years. Edward White. Okay. So that was a classical novae. How about a dwarf novae? What are they about? Very similar, but a bit different. So once again, here's your white dwarf sitting here that's compact, that's hot. Here's your big red supergiant or red giant. It's starting to lose control of its atmosphere, of its outer hydrogen because it's so big. Here it is here, streaming across here to form this big hot accretion disk. But there's something different that can go on in this accretion disk. Usually if it behaves itself, matter just goes around in a nice logical manner until it gets to the inner, and then it's turned to go onto the surface of the white dwarf. But like all things in life, nothing is ideal or perfect. And you start getting little clumps of material in that disk at random, that becomes unstable. The technical term is gravitational instability, which means instead of being nice gravitationally stable and following all the laws and so on like that, it's a little bit irregular. You get a little clump of gas that just doesn't behave itself, and it becomes unstable, and it falls randomly into the disk a little bit further along in the disk. So instead of going round and round like that, say, it might just go raise itself and go into here, or maybe straight into the white dwarf. When that happens, you're talking big distances, high velocities. We all know there's energy. If I lift this cup off here, that's potential, gravitational potential energy. That's what the weight of it and so on. And you let go and that comes kinetic energy. You're talking big energy levels. That's called, when its head suddenly inwards, you get a release of what they call gravitational energy. And there's a lot of energy packed up into potential energy or gravity. When that happens, with that sudden release of a large amount of gravitational energy, you get release of light, high energy light, as in electromagnetic radiation. I think we've got a slide here. It is, yeah. And that's your dwarf novae. Here's a little hot spot that's come in here, a little clump that's just becomes a little bit unstable, and it's probably moved just from about here to here, and you can see a little hot spot that's formed. Often during optical wavelengths, it can go down to infrared, but often it'll be so energetic, it really gives out these high energy X-rays as well. Now you might say, okay, the classical one is where the surface of the white dwarf heats up and goes bang. That's about every 10,000 or so years. How often can these form? Well, because it's just a little bit of gravitational instability, they can occur a little bit more random. They occur sort of weeks to months in known stars, but they can occur in timescales of days as well. And it's a little bit random. Some stars, their disks are a little bit more unstable than others, but you get the gist of it anyway. They're a lot more frequent and less dramatic, but just more of a quick short jab of energy, of light, that occurs, and it's a little bit more frequently, but less dramatic than a true classical nova. Here is a light curve of a dwarf nova. It's actually that SS Cygni, which I had on before from that diagram. And here you can see the light curve, so it gets bright, goes down, and we're talking on scales of days here. So it goes up, gets really bright, goes down quiet for a few days, get bright again. And now, you can tell me what's going on here. Yeah, little clumps, that accretion disk, a little bit of a clump of materials, develop some gravitational instability. It's just not behaving itself. It's fallen inwards into the disk or to the white dwarf, and that sudden release of gravitational energy, blast of light, can be optical or X-rays. So yeah, days to decades. It depends on the transfer rate. There's a lot of stuff going on there. The amount of compression, the mass of the white dwarf and so on. A lot of factors play, but you get the gist of it. So this slide here just brings that together. The two classical and dwarf novae, they're both the same process going on. You've got a central, compact, hot white dwarf with a close binary, critically close companion. It's big, you get spillover of that hydrogen from the outer shell because it's just gravitationally unstable, forms that hot accretion disk, and with the inner disk, material falls into the white dwarf hot surface, and you get that almighty explosion occurs with runaway nuclear fusion. You get your classical novae, or you get that unstable clump of disk material falling inward to release the gravitational energy, and you get that short, more frequent random burst of a dwarf nova. So that's, in summary, what novae are all about. There's two different types, the same process is going on, but just two slight little endpoints. Oh, time for another helper today. And that's the end of chapter 2. So before I got to recognize all my helpers for the day. This is Maya. As you can see, she's causing a lot of help here. Just so much work gets done when Maya walks in the room. Yeah, right. You instantly push the save button. That one. So yeah, she's a little darling. So she played a big part in today's help as well. So bless you, Maya. Okay, you'll get some extra treats tonight. Let's move on to the next chapter, shall we? Supernovae. So we've done novae. Let's move on to supernovae. And I've split it into two groups, type 1a supernovae and type 1b, 1c, and 2 supernovae. And you might be thinking, really? That doesn't seem logical. Let me show you how it is logical. Okay, you've seen this slide before. Here's your Novae over here. We'll talk about Kilonovae shortly. And I made the note here that supernovae are classified by what prominent elements are seen in their spectra when you've got your spectroscope on. And it all comes down, once again, this is all historically. A lot of astronomy things were done historically before they really knew what was going on. They made these rules up, sort of classification rules of what they were seeing. And then things didn't quite work out that way when they discovered really what was going on. But they kept the classification going on just to confuse the likes of you and I. And they do a pretty good job of doing that some days. So anyway, the bottom line is type 1 supernovae have no hydrogen in their spectra, and type 2 supernovae have hydrogen in their spectra. It comes down to that. But then you'll see here, it starts splitting up to if there's silicon and if there's helium in them and so on. You'll see here, here's your type 1a, and which is in red, and here's your type 1b, 1c, type 2, that's in black. So you can instantly see here, look, I've put a nice little line through here, core collapse, thermonuclear. So you instantly, I'd like to think you're getting, aha, I'm seeing the logic in here. It all comes down to if there's hydrogen or not in the spectrum. Don't get confused by that, but the 1As have a different process going on. And that's what we're talking about tonight. What different processes, mechanical processes, are going on to explain these events? Let's go and find out. Let's talk type 1a supernovae. So they occur, once again, another close binary. So you know what a binary system is now, 2 stars going round, close binary, they're critically close to one another. We got one of these little cunning white dwarfs in here again. They're cunning little characters, aren't they? They certainly have a very exciting life, these white dwarfs. You think, a stellar corpse, hello, it's dead. Whoa, no, these babies get up to lots of mischief. So you get them in a close binary and they have quite a little bit of fun. So if you get them in a close binary with any other type of star, including another white dwarf, trouble happens. And the key to it is that a white dwarf is perfectly stable and happy and behaves itself as long as it keeps its total mass below 1.4 solar masses. In other words, 1.4 times 2 times the 10 to the power of 30 kilograms. It's all happy. But if it reaches the critical mass of around 1.4 solar masses, things start to happen. And this can happen one of 2 ways, either repeated accretion. Remember we talked about that accretion disk, and when accretion disk, material slowly climbs onto the white dwarf, it can go supernova, goes bang, and a lot of that material is shredded off. And some of those events, not all the hydrogen gets shedded off, some of it does just get left behind and embedded into that white dwarf. So the white dwarf can, after repeated episodes of accretion and novae, just build its mass up, and it can unpredictably get up to 1.4 solar masses. And another way it can do that, if you get 2 of these white dwarfs going in a close binary and they start to merge and collide with one another, that's the second way that can happen. And that when some more sparks start flying. So let's have a look at that. Okay, here we go. Oh, that just pretty much explains it. Yeah, so the mass of the white dwarf, here's an accretion disk going on. It gets bigger, bigger, bigger. The mass goes up, and then whammo. And what happens here is the white dwarf totally gets destroyed. This is a runaway, catastrophic event or explosion. Just the total star gets demolished. It just rips itself apart. So it's a one-off event. And as you would imagine, one of these real hot compact stars just exploding itself, it's bright, as in real bright, as you're about to see. These are the brightest forms of big, bright event in the sky, transient event, whether it be a Novae, supernovae, or kilonovae. So it's a one-off explosion. The white dwarf does not supply. They all occur at 1.4 or thereabouts solar masses. What does that tell you? That tells you it must be a consistent luminosity, or a consistent, the same standard amount of brightness. It's not like you've got one white dwarf blowing up at 1 solar mass, and another one could be 1.8, another one could be 2. No. They're all perfectly stable, and there's good reason for that. That's another whole talk on its own, well beyond the scope of this, probably the scope of my physics too. So it just gets that critical level of 1.4, and it just goes, poof, it becomes unstable. It's actually because molecules and atoms and stuff start going far, well, approach the speed of light. There's the actual real reason behind it when you delve into it. Of course, that's the speed limit. So the whole thing just rips it apart. Now, so you've got a consistently brightness. And here's a little concept for you. If you observe something far away and you know how bright it actually is through, you look through your spectra, as you're about to find out what spectra involved with the 1A, you know how bright it is through your telescope, your apparent brightness. It's easy to work out the distance between the two because you know the absolute brightness of this event occurring here. So that serves as what they call a standard candle, which just as a term to describe, it's a candle of out in space in a faraway galaxy at a set brightness that you know what it is. These babies are the brightest of all supernovae, so you can see them in far, far away galaxies. So they're used as a standard candle for measuring distances to far away galaxies. And you've probably heard that they've used standard candles to measure these distances to work out the expansion rate of the universe and so on. And that's what it's all about, type 1A supernovae. So when you do see that in an article now, you say, yep, I know what type 1A supernovae are all about. It's a white dwarf that's reached a critical mass because it's merged with another white dwarf, or it's just accreted a critical amount of mass and it's gone poof. It's a set brightness and or a set luminosity at a set mass. So here is one of these light curves. Remember, you go, whoa, when you saw the Novae, what, at 100,000 luminosities? These babies, 10 billion solar luminosities. That's how bright these things are in this light curve here. So this is one here against luminosities. Here it is here, going up to about 10 billion solar luminosities, and then over the space of about 3 or 4 months, it starts to fade. So you can immediately see it's much brighter, and it lasts for a lot longer than your Novae, hence the name supernovae. So that's a 1A light curve. Give you time just to take that in. Next slide. So why this unique spectra? In other words, what you see, what sort of elements you see in your and through your spectroscope when you look at one of these 1As going off, because of course when you see it, you just see a big flash of light and you don't necessarily know what type it is, so you put your spectroscope on to have a look. So first of all, you don't see any hydrogen in it, so you're immediately going down this line, and they have a lot of silicon in them, and that's the key to a type 1A, as you can probably looking at this chart. There's no hydrogen in it, there's no helium in it, because it's going to be something else. You just tend to see a lot of silicon in the spectra, and you might say, why is that so? Well, for starters, it's a white dwarf that's going boof. A white dwarf, as we talked about, is an exposed carbon and oxygen core. In other words, that's all it is. It's just predominantly oxygen and carbon, just in this real hard core. It was once the core of a star, up to 8 solar masses. The hydrogen and the helium got long blown off over a few thousand years in that planetary nebula. Remember we mentioned the outer layers of these stars up to 8 solar masses. Just at the end of their lives, just the outer shells of the hydrogen and helium just gently puff off to form these lovely pictures that I've shown here. And don't tell me you haven't seen one of those. Everyone's seen these pictures in books and internets and thingies. Here's your little core in the middle here. That's your little white dwarf. So that's what a white dwarf is. It's just a core of carbon and oxygen. There's no hydrogen and helium, so you don't see it in your spectra. Where did the silicon come from, you may say? The silicon, hello, you've got carbon and oxygen rich environment in this huge, one of the most explosive events known in the universe, going boof. These hydrogen carbons getting rammed together and all sorts of stuff's going on. That is where your silicon comes from. So that is why they are classified. They've got their own little classification as they are. No hydrogen or helium, just silicon, and that immediately tells you what's going on. A dense carbon-oxygen core has gone boof, formed some silicon, and there's been no hydrogen and helium involved. There's only one event that will cause that. a type 1a supernova when a white dwarf goes boof at 1.4 solar masses. All good? I shouldn't talk so fast, should I? I get excited. Sorry, guys. I just love this. Okay, so that was your type 1. I'll try and talk a bit slower. Type 2, 1b and 1c supernova. And we've seen this picture before. This is most of these supernova images you see, they're taken in X-ray wavelengths, usually from the Chandra telescope or the XMM Newton telescope. That's an orbit. They're well worth looking up on. I love them. So, but this is all, and that immediately tells you these are highly energetic events. All this ejecta from this explosion heading out, so violent that X-rays, high energy X-rays are emitting. And here's your little neutron star sitting in the middle here, giving off X-rays as well, because it's so damn hot and energetic. So let's have a closer look at these supernovae. Here's this famous picture again that looked a little bit odd and messy, but hopefully you're starting to see some reason behind it all now. So here was your type 1a from your white dwarfs. We're starting now going to go into massive stars and have a look at this. Yeah, they're all the result. These 3 type of supernovae, instead of a white dwarf, they've got something in common. They're all a one-off, which all supernovae are, the star gets destroyed, a one-off core collapse of a massive star. It's got a big massive star, a little core in the middle, and that core collapses. We're going to have a look now, and why does that core collapse? Let's have a look into that. And of course, you know now we're talking about solar masses of more than 8, because you saw those diagrams early on a few times. So, yep, they're all the result, a one-off core collapse, a massive star, greater than 8 solar masses. So you instantly, when you look through your spectroscope, when you see one of these big explosions and you start to see hydrogen and helium, you know it's not a white dwarf that's going on, because they've long lost their hydrogen and helium. You know that a massive star greater than 8 solar masses has just gone, its inner core has just collapsed, it's gone supernova, which we're going to talk more detail now. So I thought the best way of approaching all of this without me getting too excited and talking quickly and flapping is answer these 3 questions, which I will. Where does all this sit on the stellar evolution chart? So I'm going to bring that chart up again. You're never going to lose sight of that chart as long as I'm talking. Why do these massive stars explode into supernova, as they do? And why the crazy looking classification, which I would like to think you're already starting to get a feel for now. Here is the stellar evolution chart again. Hopefully you'll see this in your sleep tonight when you close your eyes. There's just your average star up to 8 solar masses, including our sun, puffs out to red giant when it leaves the main sequence. Then its outer layers puff out like that, hydrogen, helium, to leave the exposed, hot, dense, compact core of oxygen and carbon. Here's your massive stars, 8 solar masses onwards, turn into red supergiants, and they go boof at a certain time, which we'll talk about. Remember, if it was 8 to 20 solar masses, the central core is a neutron star. Greater than 20 solar masses, the central corpse is a black hole. So that really should be well and truly up here by now. If not, you can watch it again later on. Here's the Cassiopeia. That's a pretty cool image, isn't it? X-ray image. Spot the central neutron star. Woohoo. There it is. The early X-ray images, they couldn't see it. The resolution wasn't there. And it's really just been the resolution over these more sort of modern X-ray telescopes over the last 20 years or so. They've had the definition and the resolution there. And they're actually seeing these neutron stars in the middle for the first time. I just think that's a cool picture. So why do these massive stars go supernova? And it's because, and I'm going to explain it all shortly, but because nuclear fusion in their cores stop, so the core collapses. So let's go into a bit of depth here. A little bit of revision is that in stars, 90% of their lives, they're nice and stable, what we call equilibrium, a hydrostatic equilibrium state of that, and whereby in the central core, well, let's actually start from the outside. They've got a certain amount of mass, and that mass with gravity is driving down onto the center of the star, into the core. The pressure and the temperature rise in the core. Hydrogen starts fusing into helium under those conditions. And of course, that generates energy. And the energy from the core nuclear fusion pushes against the force of the gravity pushing down from all the outer layers. And that reaches a steady state. It's a balance. Hydrostatic equilibrium. That's the term that they just used to explain that. And that occurs, that going inside a star, and it's by definition the main sequence of a star when hydrogen is going to helium in its core. and then it leaves the main sequence and it turns to a red giant and so on. And that's where helium turns into carbon, into neon and oxygen and so on. And a star up to 8 solar masses, of course, only goes to carbon and oxygen to form that core and the planetary nebula. But the big stars keep going. The big massive stars, more than 8 solar masses, they have enough material pushing down on that core to create enough gravitational forces, just keep driving the pressures and the temperatures up in the core, whereby when it's finished burning hydrogen to helium, let's have a look here, they form a little hydrogen shell. It's another talk. We actually did a lot of this with stellar evolution, but we can do it again another time. It's all good. Life is good, guys. Helium starts burning, then you get an outshell of helium that forms into carbon, and you get neon burning, and you end up with this multi sort of like an onion layer, if you will, of different layers of shells of different elements all there. And each time it moves on to the next one, and so on and so on. That nuclear fusion, once again, just when you're combining 2 smaller elements to form a bigger one, nuclear fusion, it generates energy and it pushes out, and that keeps the star propped up. But here's the catch. With these big stars, they keep pushing it and pushing it until suddenly they've made iron and nickel in their core. And iron and nickel is interesting. They are quite inert, such that instead of when you try and fuse them, instead of liberating energy, suddenly these guys absorb energy. They want to take up energy. So instantly you've got this core that's doing nuclear fusion, propping itself quite happily, thank you very much, against the forces of gravity around it. And suddenly iron forms. Iron can't be fused. It suddenly wants to suck all the energy up. So the core just collapses like that. And that's called core collapse. Remember we talked about here, all these are because nuclear fusion and their core stop, you get core collapse. That's why the nuclear fusion stops. You reach iron, and iron, you try and fuse it. It doesn't give out energy. It sucks energy in, so the core collapses. And all these stars greater than 8 solar masses, they get up to iron, and that's where they fall apart. Well, quite literally, actually, the core collapses. So here's another little one here. Here you go. Here's a big red supergiant. Here's your core with all your different onion layers, if you will, burning through till it gets iron core. No fusion can occur. The core collapses. What happens then? Instantly, within nanoseconds, that huge, massive, big supergiant. Remember I told you that if you put one of those babies like Betelgeuse in our solar system, where the sun is, its surface would go out to the orbit of Jupiter. These are big mothers. And instantly, within fractions of a second, you got all that mass just going wham. It just starts rushing inward, all these inner layers just keep pouring in and in as the whole star is collapsing. And all that instantly comes up against that hard, compact core that's just collapsed, hits it hard at God knows zillions of kilometers an hour, and instantly rebounds off. So you've got material coming in, you've got other material hitting it, it's coming out, you're getting one heck of a mess going on there. High velocity, high compact, high energy, mess, explosion, extreme forces involved. Hey, there's your supernova. That's how they happen. That's why they're called from a core collapse. And it's your type 2, type 1b, and type 1c. So you can start to see the logic why you classify supernovas as you do. 2 totally different mechanisms. Your 1a, a white dwarf that reaches a critical mass, becomes unstable because all its particles want to travel up to the speed of light, so it just blows itself apart. And these babies here, we get core collapse. And what we're going to do now is talk about, well, why you're probably saying to yourself, I get all that. But how about why 2 and 1b and 1c? Let's have a look. Okay, let's bring this diagram up. So here it is here. Here's your core collapse, your 1b, 1c, and type 2. And notice here, here's your hydrogens, that becomes a type B, and that's all for historical reasons. Just keep that in mind. Now, to make sense of this, we need to now consider the outer layers of stars. What happens to the outer layers of stars when the stars get more massive and larger in size? And this is the key to it all here. This is exciting. I love this stuff. Love it. Okay, so as a star starts getting bigger, it starts becoming less capable of retaining the outer envelopes or layers, if you will, of its light elements. Remember, the heavy ones in the core, like anything, tend to be in the center, and the lighter elements, hydrogen and helium, will puff out and they're lighter. So you've got less control over lighter things anyway. But remember, your surface gravity with a big star, your surface gravity is not as strong because you're further away from the center. And the other thing I mentioned is you can get shells of nuclear fusion, of hydrogen and helium fusion, in some of those outer layers of these big red giants. And that's a force in itself. So needless to say, you've got big, strong stellar winds. In other words, high energy just driving, just ripping the star apart. So these stars, as they get bigger and bigger, they get less and less capable of hanging on to the outer shells of these light elements, such as hydrogen and helium. So what I've done here, I've got my little bits and pieces out. I'm sorry about my artwork's not the greatest, but anyway, I drew some circles. Here's your main core. Here's a star of solar masses from about 8 to 40 solar masses. It's small enough whereby it can, stars up to 40 solar masses are okay. They can hang on to the helium and the hydrogen outer shells. So when that star goes through its core collapse, when iron forms, and it tries to have a crack at trying to fuse some iron, but it can't. So your core collapses and you get that rush inward and you get your supernova. If you're over here watching that, you are going to see, and what are you going to see in your spectrum? You're going to see heaps loads of hydrogen and some helium in there, aren't you? So that's in a star of 8 to 40 solar masses. Consider a star of mass from about 40 to 60 solar masses. The 40 you often see in literature, but the 60, I've put the sort of approximate symbol here because do not quote me on 60. Every source you look at is different. I've just put that in for a guideline for you, just an arbitrary figure. So let's just consider a star, say 50 solar masses. It's got strong stellar winds, and it's of large enough size where its surface is far enough out from the middle where the surface gravity is getting weak as well. It's this nuclear fusion in these outer shells. So you tend to blow off the hydrogen before it gets to later stages of life. So when the core collapses in here, because iron can't be fused, and the whole lot collapses inward and goes boof into its supernova, if you're over here with your spectroscope looking at it, you're not going to see any hydrogen in that because the hydrogen's long left town. It's been blown off, a few thousand years before it went supernova, but you're going to see a lot of helium in there. How about you go at arbitrary, let's say above 60, let's go say you've got a star of say 80 to 90 solar masses. That's also got nuclear fusion going in its outer layers. Its surface layers are so far away from the center of the star, the surface gravity is even weaker, and that star has usually lost most of its hydrogen and its helium outer layers. So when it goes boof in a supernova, you're not going to see any hydrogen or any helium going on there. And here's your classification, guys. Remember, here, if you're up here looking at this smaller one, you just see hydrogen in the spectrum. What did you learn from that little graph back there? Let's go back a little bit. All you see is hydrogen, type 2. Here, you've got your one, you've just seen helium, you're seeing no hydrogen. Let's go back here. No hydrogen. Helium, type 1b. Yay! There it is there. Okay. Here's your one here. You look at this big mother of a star here, say 90 solar masses, for example. You don't see any hydrogen helium because it's blowing it off. So what do you see? Let's go back. So you go, whoa, there's a supernova. Oh, I don't see any hydrogen, so I'm going down this branch. Don't see any silicon because it's not a white dwarf. I don't see any helium, so I've gone down this route here. It must be a type 1c. So you instantly know, hey, I've just seen a big star of about 80 or 90 solar masses go boof. You know, because you've looked at the spectrum of it and you've seen what elements are in the prominent elements in the spectra. So already you're starting to see there actually is some sense behind all of this. Hypernova, new term. Whoa! You think, what on earth? I've seen the word hypernova. Where did a hypernova fit in this? Well, let's have a look, see. A hypernova refers to a really, really, really big mother of a 1c type, whereby, it's not well understood, but whereby the star is so massive that for unknown reasons, instead of it all just going supernova and spreading out sort of like in a global type of pattern like there, the ejector of matter and the energy tends to go out in bipolar jets in line with the rotational axis. Not fully understood, but what they do notice is they get a gamma ray burst. You recall from our talks on light and so on that the gamma rays are the most powerful, strongest forms of light or electromagnetic radiation there is. And you get these sudden bursts of these really high energy gamma rays. I don't know if I can't remember if I've given a talk on gamma ray bursts. I've got a talk up my sleeve there on gamma ray bursts. So gamma ray bursts are divided into long duration or short duration. And a long duration one is anything that's more than about 2 seconds. These guys give out long duration gamma ray bursts. Interesting enough, you're about to meet some short gamma ray bursts shortly with neutron stars. So stay in your seats. Don't tune out. So that's a hypernova. If you see that term hypernova, you think, yeah, okay, that's a type 1c supernova from a massive big mother of a star, but this is a really, really, really big one, and it's just formed this type of explosion through really, they're still trying to work out the astrophysics behind of all of this. Okay, so here's some examples. You've seen a big flash in the sky of some light. You slap your spectroscope on and you start recording it. So what do you see? Let's have a look at this star here. This is a type, well, let's have a look at it. Oh, lots of hydrogen going on here. Hydrogen alpha, beta, gamma going on here. These little sort of little dips in here, meaning there's hydrogen in the atmosphere and the outer layers of that supernova explosion that's going off. So what does that tell you? It's type 2. What does that tell you? It's a massive star from about 8 to say 40 solar masses. Isn't it neat how you're finding this information out just through your telescope with a spectroscope on? What say you looked at this one here and you say, what's going on here? Oh, there's no hydrogen here, so it's not a type 2. I'm seeing a lot of helium. Ah, that's a type 1b. What does that tell me? Oh, that tells me that a big massive star from about, say, 40 to 60 solar masses, its core has just collapsed because suddenly it's tried fusing iron and the whole lot's just gone boof. It's collapsed and would rebound and gone boof. We know that because there's no hydrogen in it, so it must have blown off the hydrogen before. You knew that just from looking at the spectrum. Okay, here's another one. You look at this one and you think, oh, okay, what's going on here? No hydrogen, no helium to talk about. A little slight mention of silicon, but nothing to really mention. Hey, what is it? It's a type 1c. So you instantly know this is a big, massive, maybe sort of 70 or 80 solar mass star that's reached the end of its life. It's gone, its central core has collapsed. Isn't this neat? It's really cool. You can just tell from your spectra what's going on, what the star was like, what its progenitor was like. Progenitor is a cool word. Progenitor in astronomy means what was the original star there before this event. So it's telling you, you're looking at a big explosion, a big messy mess in the sky. You're putting a spectroscope on your telescope and you're instantly finding out what the progenitor was, what the original star was, how big it was roughly, all through some good science, observational astronomy. Hey, have it this one here. You put this on a big boof in the sky. You think, jeepers, that's a big bright one. No hydrogen, so it's not a type 2. No helium, lots of silicon, type 1a. You know that was a white dwarf in its time. You know that was originally from a star somewhere between 0.8 and 8 solar masses. You know that over a few thousand years, eventually it shed its outer layers off, central white carbon and oxygen core that then even accreted some mass or collided with another white dwarf. Critical mass is gone boof. You know that just by simply looking at the remnants of the explosion. How cool is that? Admittedly, I get excited by these things. Let's have a look at some light curves of supernovae. So this looks a bit messy, guys. I appreciate that. But look at this. The main point here is taking that, each different type of supernova. So here's black 1A and there's red 1B and so on, and yellow 1C and so on. You get the gist of what's going on here. See, there's little different subgroups. Don't get bogged down by that. There's just 4 main types that we need to worry about tonight. So the bottom line is, as you can see here, they're all slightly different. They're light curves, how quickly they go up, how high they go up, and the nature of where they go down. So in other words, yes, you can look at the spectrum, but there's more clues to what's going on too by the, what sort of light curve does it fit the model sort of light curve. And the other thing here is look how much brighter the 1As are. Remember, these were your standard candles. You knew the critical mass of the white dwarf because they reliably go boof at 1.4 solar masses because the particles are getting so crushed together that they're approaching the speed of light and the laws of physics just falls apart. So you know that. So you know you're seeing how bright it is. They're so bright. They're seen at long distances. You measure how bright it looks from us. We know how bright it is. You work out the distance to that faraway galaxy. So that's pretty cool. Supernova are important, not only because they're cool things to look at, but those explosive forces, and this is a whole talk, which I'm going to do the one after stellar corpses. So in 2 talks time I've got up my sleeve is a talk on nuclear synthesis. In other words, how elements are formed. You've probably already gone over, but I'm going to go through. I consider there's 3 stages. There's one at the Big Bang, and we'll talk about that, formation of hydrogen, helium, and some lithium and barium and so on. And then there's in the core of stars, you've seen there's oxygen and carbon right through to iron. You pretty much have seen that's been thrashed over and over to you. But where do all these heavy elements come from? They come from these explosive forces that are going on. But instead of being fused together by nuclear fusion or thermonuclear fusion in the cores of stars, they form these supernova explosions are full of particles, in particular neutrons and protons. Particularly if you've got a neutron star in there, they're rich in neutrons. And suddenly you've got this explosive force going on with particles just being rammed together, left, right, and center. You're getting these smaller atomic nuclei as the building blocks, but they're quickly accumulating neutrons and sometimes some protons, and the neutrons are decaying. All this messy stuff is going on. It's a whole talk. I love it. And you get what they call neutron capture process going on. And there's R, there's S, there's P neutron captures. But the bottom line is, it just refers to the rate at which beta decay, what a neutron, when it spits out on a high-speed electron, it forms into a proton, and so on. So we'll have so much fun talking about that. But my point being is you get this process of neutron capture, where these smaller nuclei start building up neutrons because of the huge forces involved, and they get up to a certain point. So that's how these heavy elements get formed in these big supernova explosions. So the supernova does 2 important things. One, it creates all the heavier elements than iron, but 2, it then distributes them throughout the galaxy. Poof, just sends them on their way. Go out, guys, go out, create a solar system, create some crazy guys called humans who are just going to party all day and have fun talking about us. That's why supernova are important. Who said astronomy wasn't exciting? Okay, chapter 5, Kilonovae. So we've done novae, we've talked about classical and dwarf novae, we've talked about supernova, the 2 main mechanisms for those and how to determine them. Kilonova, they are from, it's a compact binary system. Notice how a lot of interesting stuff happens when you get these stellar corpses and binary systems. And a kilonova is from the merging of 2 neutron stars in a tight binary system, or a neutron star in a black hole. It'll do the same thing, a kilonova. Let's have a closer look and see why. So these explosive events, they release even heavier radioactive atomic nuclei than your supernova. Why? Because you've suddenly, what are neutron stars? Which we'll talk about next month or the month after, the talk I do after this one, stellar corpses. They're really dense. The neutron stars are just full of neutrons, really ram-packed together. So suddenly you've got this explosive event going off, high concentration of neutrons. So you build up these large atomic nuclei. But the nuclei get so big, they become radioactively unstable. So they start tearing themselves apart off and just flying out pieces because they're just too big. They can't hold themselves together. And in that process of radioactivity, energy gets released. And that's what we're seeing when we see the kilonova. We just see these high atomic nuclei form. They're decaying because that R process here that I mentioned a couple of slides ago, the rapid process, they clear quicker then they can decay. So this is getting bigger before the laws of physics start causing radioactive decay. They get to a certain point that really heavy, unstable, they really then start firing out energy, and that's what we see as the kilonova. So what happens then, you see the energy is so energetic for that first split second. This is your high energy short gamma ray burst. In other words, a gamma ray burst less than 2 seconds. Like, what was that? Short gamma ray bursts. They come from these neutron star mergers, really intense, but they continue to glow in optical and infrared wavelengths for usually about 10 days or so, go from there. Okay, so how bright do they get? 1,000 times bright as your typical classical nova, hence the name, kilo. Kilo means 1,000. A kilonova is from 2 neutron stars merging, and its maximum brightness is about 1,000 times that for classical nova, which equates to about 1/10 or 100th of a supernova. In other words, it's not as bright as a supernova, but it's 1,000 times more than a nova. Their light curves, I've made a note here, very diverse. All sorts of modeling and stuff going on. But the cool thing is, if you get some information from the light curve, you can combine that You probably remember sort of about the last 5 years or so, they've been studying gravitational waves, and there's been talk of how neutron stars and black holes start getting closer and closer together, going round and round quicker before they merge. The energy of that, as they come together, gravitational energy gets dispersed with little ripples in the fabric of space-time, and that's your gravitational waves. They can measure those gravitational waves, record them, analyze them, mix that in, immediately see where it came from, and look for the kilonova, and analyze the light curve, and they can once again have a closer look at what those progenitors were, how they've come together, what's the post-merger evolution, what's left on afterwards, and that's how it is all done. Here's the Hubble telescope, its very first nova that I observed in 2017. That's it there. And you can see there's just a few days, I think, having a close look, August the 22nd, 26th and 28th. Here it is there, a few days apart. So you can see that right there. So that's the first sort of in optical wavelengths of a supernova in 2017. I think it was about 2015, I think, if I recall rightly, that they first picked these things up with gravitational waves. So, as I mentioned, kilonova also important source of these heavy elements, because you look here, here's your exploding massive stars and white dwarfs and green and blues here. So all the heavy elements tonight, and that's cool. But you think, well, what's going on down here, guys? There's a lot of other colors going on down here. A lot of it's your merging neutron stars is behind that. And look, they make up most, they sort of are responsible for the building nuclear synthesis of most of the heavy elements, all your gold, your platinum, and your silver. It's these merging neutron stars that are responsible for that. How to be continued, that's another talk. Okay, Stella, my third helper today. And I think at this stage, I think this was hint, Stella. I got up to do something and I turned around within a nanosecond and my chair got stolen. So I had to sit on a wooden stool, didn't I? But I think it was messaged from Stella saying, Dad, wrap your show up, put your final slides together, and then go up and feed me, would you please? So that was my third little helper today, Stella. She's a little honey as well, bless her. So tonight, let's wrap up. Stella gave me the hard word, so I wrapped it up. So what you've seen tonight, Novae just means new star, historical term. Your nova is split into classical and dwarf. They both involve a white dwarf and a close binary, and they reoccur. They're not one-off events. Your type 1 supernovae is a white dwarf and a close binary. Once again, it's a singular event. It's when the mass gets up above that critical 1.4 solar masses. It gets unstable, it blows up. Singular event, star gets destroyed, catastrophic. Your type 2, 1b, 1c, that's from a massive star greater than 8 solar masses, whose core is just collapsed because iron does not create energy when you try and fuse it. It's catastrophic, it's a singular event. Kilonova is the merging of two neutron stars and once again close binary, or a neutron star and a black hole in a close binary. You can see the relevance why I started driving that whole thing earlier on about what stellar corpses are in a nutshell, because you know these terms by now. And you can always go back after this presentation, replay it again, and just to get the gist of it, let you know it's in there early on what these stellar corpses are all about. And yeah, they lead some crazy lives, these stellar corpses, so which we'll learn about in another talk. So what are you going to tell your friends when you finally close up from here tonight, or you wake up in the morning? What are you going to tell your friends? You're going to tell them that Novae, Supernovae and Kilonovae are different beasts. Do not get led astray by what you see in the media. And there are 4 main types of supernova. Should you have any friends still left over at this stage, you can also tell them the 4 main types are split into type 1 into 2 main mechanisms. You type 1a from exploding small white dwarf, or type 2, 1b and 1c from a collapsive massive star. So when you have some quiet, I like to throw in a slide, just give you something to do, something to think about. So get your pen and paper, jot down Supernova 1987A. Go and Google it, have a read up, which is when you get a quiet moment, and look and find out what it was about, how bright it was, what galaxy was it in. And I think you'll find actually it was fairly close to the Milky Way galaxy. So a little bit of homework for you there. Okay, yeah, and look, hey guys, thank you for it. I hope you've enjoyed Novae, Supernovae, and Kilonovae. What's the difference? Thank you for watching, and I think it's about time now, our competition, which we have a winner for, Name This Pioneer Astronaut competition, and the answer was, what? Boston beat it. Sorry, guys. How did that get there? Boston. I saw him this afternoon. He was slinking out of the office. I wondered what he was doing in here. He's such a bad behavior. I don't know where he gets it from. He's always in trouble. Where does he get that from? I've brought him up here. I'm sorry, guys. He's a mischief. I love him to bits, though. Oh, Boston. Here you go, buddy. The answer's not Boston Benton. Name this astronaut. It's Edward White, first American spacewalk. This was in the Gemini 4 mission on the 3rd of June, 1965. First American spacewalk. It's worth reading up about. Sadly, Ed White was killed in the Apollo 1 fire on Friday afternoon of January the 27th, 1967. He was one of the 3 astronauts, very sad and tragic. So he was certainly very much a pioneer astronaut, dearly loved. Okay, guys, so questions. Are there any questions there at all, James?
Yeah, I've got a couple here.
Yeah.
So the first one from Ben is, when we look at luminosity, does L0 equal the brightness of the sun?
Yes, yeah, Ben, good question, Ben, and I should have pointed that out. When you see that little 0 with a dot in the middle, like a bullseye, as a subscript next to L, it means the solar luminosities. Like you see 10 L with that little subscript, 10 luminosities. Luminosities, that's a great word, isn't it? It's up there with marmalade and refrigerator and orthosite. And same with solar masses. You'll see an M with a little bullseye, subscript bullseye, a little dot with a circle around it. And that refers to solar masses. So good question, Ben. I should have made that a bit more clearer. Yeah, very good.
Okay, another question comes from John. If you go back to the slide with the table of elements.
Oh, yep. Yep.
Yeah, he wants to know what is going on with 43 technetium.
Good question. I'm glad you asked that question, John. You've just created some homework for yourself, my friend, and you can let me know. I've just spotted that too. Oh, look, the honest answer, what I'm trying to say is I'm unsure. I think that's worth looking up sometime. I certainly will be happy to look that up, and so should you, John, too. Yeah, I didn't spot that. Good spotting. Unsure. Good question. If you're trying to catch me up, you got me.
I can actually answer that one.
Oh, there you go, James. Tell me.
So
tell me, James.
There was always a hole in the periodic table, and sitting right there at 43. So, in fact, 43 technetium is the very first man-made element. So it's a non-naturally occurring element. It's purely been made in a lab.
Wow. And that would explain it, obviously. Yeah, that totally explains it. Thank you for that, James. I've learned something good there. No, thank you. Right. I think we're all good from my point of view. So, and I always like to leave, guys, whatever you do tonight. Oh, dear. You know what I mean. Be safe. Look after one another. Have fun and all that sort of stuff. So, shall I sign off then, James?
Yeah, that'll be fine. Yeah, just to say thanks everyone for attending. It was really great to see all of you there. Don't forget, we will be having these regularly. So next one is probably about 2 weeks' time. I'm not sure what we have got planned for that one yet. I do know we have a number of other guest speakers coming up, so just keep an eye out on the Facebook page or the emails, and we will definitely get that sorted out. So yeah, thanks everyone. I'm going to stop the stream now. Chris, if you hang on there for 1 sec.
Yep.
And yeah, hope you all have a good evening there. Good night.